So in this class, we will discuss about an important law called Newton's law of viscosity. In the earlier lecture video, I have explained about the different properties of fluids: specific mass, specific weight, specific gravity, dynamic viscosity, kinematic viscosity, surface tension, capillarity, all those things, with stating their definitions, units, and dimensions. Now here, one of the most important properties of a fluid is viscosity, which we don't expect in solids. So viscosity is the resistance to flow. It's a measure of resistance to flow. Newton has given one law. It states like this: in a fluid flow, the shear stresses exerted between the adjacent moving layers is directly proportional to the velocity gradient between the layers. So you have to understand this. Now to understand that, I will consider a fluid flowing in between two plates, out of which one plate is fixed plate, that means velocity is 0, and for the other plate it is moving with the velocity v. So let us assume that this fluid is flowing in layers, something like this, in layers, smooth layers. That type of flow is called as laminar flow. So what happens here, since this is a fixed plate, whatever fluid particle is adhering to this fixed plate, its velocity will be 0. But this plate is moving with a velocity v, constant velocity or steady state velocity we can say. So in between these two, velocity is 0 here, velocity is v here. In between these two plates, if you consider layers, laminae, we can call it as laminae also, the velocity will be varying from 0 to v. So that variation, I can take it as a linear variation, as a straight line. If you plot a graph of velocity versus distance from the fixed plate, I am going to take it as y. So if you plot a graph of v versus y, it is a straight line. So initially it is 0 here, then later on it increases up to the value v. So in such a case, what happens? Flow will occur in this direction. The shear stress which is going to develop as a resistance, it acts in the opposite direction of flow, like this. So in between the layers, you will be having some values of shear stress which opposes the motion. That value of shear stress is directly proportional to the velocity gradient between the two layers. So velocity gradient is velocity difference. Velocity difference divided by that distance, that is called as gradient or slope. So this is the mathematical representation. Tau is directly proportional to dv by dy. This can be expressed in terms of an equation by introducing a constant called mu. So tau is equal to mu into dv by dy, where this mu is called as the dynamic viscosity of the fluid which is flowing in between the plates. And the dynamic viscosity is expressed in Pascal second or Newton second per meter square in SI units. Now, tau is equal to mu into dv by dy, that is called as the Newton's law of viscosity. Newton has proved this by conducting experiments. Now, if you take this equation, mu becomes tau divided by dv by dy. Tau is normally expressed in SI units as Newton per meter square, and dv by dy, so you can see here, this dv is velocity meter per second and dy is in meters, therefore it becomes per second. So r second power minus 1. So you can write this as Newton, the second goes to numerator, divided by meter square. So this Newton per meter square is nothing but Pascal. So Pascal second, that is the SI unit of dynamic viscosity. The dynamic viscosity can also be expressed in another form called poise. So the conversion is 1 Pascal second is 10 points. Now as y reduces, so that means if the distance between the two plates here, whatever I have taken, so it is very small, then this dv by dy can be equated to v by y, where v is the velocity here and y is the distance between the two plates. So in that case, this dv by dy can be replaced by v by y and tau becomes mu into v by y. So here the meaning of this is shear stress is more in real fluids as mu value is very high in case of real fluids. You know that viscosity as a resistance to flow is very high in the case of thick oils. Thick oils are examples for real fluids. So in that case, shear stress developed also will be very high, because when mu is high, tau will be high. Now this Newton's law of viscosity can be applied to solve some problems on fluid flow. So one of the two examples I have shown here. One example is, you can take a block of weight W sliding on an inclined plane which is making an angle theta, and this block will be having contact with this inclined plane with the help of a fluid. So some fluid is there here. So that means some area of contact will be there of that block with this inclined plane, and between that space a fluid is filled. Then let us take that mu is the dynamic viscosity of that fluid, and weight of the block is W. This block automatically, due to its own weight, tries to slide down the inclined plane. So with some force and velocity, that force with which it slides down, that is F, and the velocity, constant velocity with which it slides down, that is V here. In such types of problems, you may be asked to find velocity or viscosity or that inclination. Other data will be given. That is one type of problem. Second type of problem is, you consider a rotating shaft. This is a shaft, and this is the sleeve. Sleeve is nothing but the opening. So in between the shaft and sleeve, you have a gap here, and that gap is filled with some fluid of viscosity mu. And what happens here, when the shaft starts rotating, some power will be lost. So that when the shaft starts rotating with some velocity, that n or in RPM, so that can be converted to corresponding tangential velocity or linear velocity v, and some power is lost during this process. So you may be asked to find the velocity or the power, all those things. So small d is the diameter of this shaft, and capital D is the diameter of the sleeve. So this small gap is filled with oil. So lubricating, in your lubrications in machines, this type of problems will come into picture. Now, when you are solving problems with by using Newton's law of viscosity, you have to stick on to the units. So SI units are very, very important. So you should know the units, because in fluid mechanics, major thing is particular, correctly you have to write the units. So here, these are the units we have to follow. F is the force, which is expressed always in newtons. A is the area of contact, it is expressed in meter square, because please note that in SI units, Newton, meter, second, and kg for the mass. So they are the SI units. So Newton is the SI unit for force, the second is the SI unit for the time, kg is the SI unit for mass, and meter is the SI unit for length. So whether it is in millimeter or centimeter, so you have to convert that into meter square or meters. Now mu is the dynamic viscosity, it is expressed in Newton second per meter square or Pascal second. Tau is Newton per meter square, which is nothing but force divided by area. So with whatever force this object or this block is sliding, so that divided by the area of contact. So A is the area of contact with the fluid. So that area we have to take. That F by A gives the value of tau, shear stress. Then velocity will be in meter per second. Distance will be in meters. If it is given in millimeters, you have to convert it into meters. Then the speed of the shaft, whatever is there, is in RPM, so revolutions per minute. And due to that, there will be development of a torque. So torque will be developed here. So this torque T is given by F into d by 2, that is radius. So this is your d by 2. So when that force is multiplied by the radius, you are going to get the torque. Torque is expressed in Newton meter, F is in Newton, D is in meter. Then power lost is expressed in watts, which is given by 2 pi nt by 60. So here N is in RPM, T is in Newton meter. So if you use that, you will be getting P in watts. The watts is the SI unit for power loss. And sometimes they may give the rotation in terms of angular velocity, so radians per second. Angular velocity is expressed in radians per second. So when the angular velocity is multiplied by the radius, you are going to get the linear velocity in meter per second. So these are the SI units you have to follow when you are analyzing a problem on Newton's law of viscosity. So it is very, very important to stick on to the particular SI units for any physical quantity. Otherwise, you will get erroneous results. Now, I will take up a problem of this type. First type of problem where you can see here there is an inclined plane. This plane is making an angle of 30 degrees with the horizontal. There is a cube. So one cube is there, is placed on this plane whose mass, he has given the mass of that fluid. So mass of that object, mass of the cube is 10 kgs. He has not given the weight. So we know that mass into acceleration into gravity gives the value of weight. So 10 kg is the mass of this cube, and there is a gap of 1 mm between this bottom surface of the cube and this inclined plane, which is filled with oil. Oil of dynamic viscosity 0.025 Pascal second or Newton second per meter square. Now this is the problem, practical problem. Now the question is this: we have to find out what is with what steady velocity this block starts moving under its own weight. So there is no other external force is acting on the block. Only weight of the block is there. Now the cube has a side 300 mm, that is 0.3 meter. Now let us see how we can use this formula to solve that problem. So V is the unknown here. We have to find out the steady state velocity with which that block starts moving. Now first I have calculated the weight of the block, which is m into g, because mass is given. You have to multiply that by 9.81 to get the weight. Suppose if they give the value of weight in Newton directly, you can take that. Sometimes they may give the weight value in kg force. 1 kg force is 9.81 Newton. So you have to convert. Suppose if the weight of the block is given in kg force, you have to convert that into Newtons 9.81. Suppose it is 10 kg force, then 10 into 9.81, like that you have to take. Now here, F is the force acting on the block downwards, because due to its weight, it starts moving down. That F we have to find out. So there is no other force acting on the block, only weight of the block we have to consider. Please note that weight of the block always acts downwards, vertically downwards, which is 98.1 Newton. Here it acts downwards. So F is acting in this direction along the parallel to the plane. So we have to resolve this W into two components, one along the parallel to the plane, another one perpendicular to the plane. So parallel to the plane, if you analyze, this angle is 30 degrees, so therefore F value becomes W sin 30 or W cos 60. So both are same. So that is the force with which that block starts moving. So W sin 30 is 0.5, so it becomes F becomes 49.05 Newton. Now what is the contact area? Contact area of this cube. So this cube has a side of 0.3 meter. So 0.3 by 0.3, that is 0.09 meter square is the contact area. Now as I already told, when this force is divided by the contact area, you are going to get the shear stress that is going to be induced. So shear stress acts in the opposite direction to the direction of motion. Direction of motion of the block is downward. Shear stress acts upwards, just like friction. So this F by A is 49.05 divided by 0.09, which comes out to be 545 Newton per meter square. Now we can apply that Newton's law of viscosity. It states that since here this y is very, very small, 1 mm is very, very small distance between that block and this fixed plane. So it is 1 mm. So you can write tau is equal to mu into v by y. When y is very small, you can use this. Now here v is the unknown, so v becomes tau into y divided by mu. So everything should be substituted in SI units. Tau is 545 Newton per meter square into y is 1 mm means it should be converted to meters, which is 0.001 meter. Be careful there. Divided by mu value is also in Pas per second means it is in SI unit. Directly you can substitute 0.025. You simplify that, we are going to get the velocity value as 21.8 meter per second. So 21.8 meter per second is the velocity of that block, steady state velocity of that block, through which that block slides down the inclined plane. So this is how we can solve a problem using Newton's law, viscosity. So here the different parameters, or these are the parameters. So in the next video, I am going to explain a problem of this kind, shaft within a sleeve.